This is one of my favorite tapes. It is a tape of what you might call enrichment topics. Some topics that may have been left out of the course that you'd like to see, or some things that usually aren't shown to people in college algebra, but which I think you might find interesting. I call them the XY files. The proof is in here, and I hope you enjoy them. Now, on this X-Files tape, what I've done, as you see at the top of your screen, is I've written for Unit 0. And for other slides, I will write for other units. So you'll have an idea where the segments within those slides actually apply to the course. So the first thing we'll look at here under Unit 0 is a proof that square root of 2 is irrational. You may never have actually seen a proof of that, so I thought I would include one here. So let's see how this would go. There is a theorem, square root of 2 is irrational. Here's how the proof is going to go. We're going to say, we're going to do this proof by way of contradiction. Now this is usually the way one proves that something is irrational, because rational is a proper definition, but irrational is simply all the real numbers that are not rational. So how would you go about approaching that? The traditional way is to do it by contradiction. We will assume that square root of 2 is rational, and then we'll try and get a contradiction from that. So, by way of contradiction, let us assume that square root of 2 is rational. Well, what does that mean? So, that means that the square root of 2 is equal to p over q, where p and q are natural numbers. After all, we know the square root of 2 is positive. We don't have to worry about negatives. And of course, it goes without saying, although I'll mention it in case anyone wonders, that q is not 0. Of course, 0 is not a natural number. And we will assume, so we've assumed this, that p over q equals square root of 2, and that p over q is in lowest terms. Lowest terms. Which means p and q have no factors in common. Okay, this is going to be very important to our proof. Have no factors in common whatsoever. Okay, so that will be very important for our proof. And having set this up this way, now we will sort of follow our nose and see what happens. Then, let's just write down what we've got. We've got square root of 2 equals p over q. Well, one thing I can do is multiply both sides by q to bring the q up. So I have square root of 2 times q is equal to p. Now I don't like the square root symbol, so I can square to get rid of that. So if I square both sides, I have square root of 2 times q squared is equal to p squared. On the left, I get 2q squared is equal to p squared. Now here's our first observation. Notice that 2 divides the left-hand side. So 2 divides left-hand side. That's my abbreviation for left-hand side, LHS. So since it divides the left-hand side, it must, since the right-hand side is equal to it, must divide the right-hand side. So 2 must divide the right-hand side. But the right-hand side here is p squared, which if I were to expand it is p times p. So where would the 2 divide? It must therefore divide into p, which means, p is even. So it has a factor of 2. Okay, we've observed this from our little argument. Let us continue. If p is even, we can write it as 2 times something, and then we can continue from here and see where that leads. So we can write p equals 2 times r. Because it's even, it can be written as a 2 times another natural number. And then we can continue. We had previously 2q squared equals p squared. Well, now p is 2r, so let's just go ahead and substitute that in. Well, we can square that right-hand side. So repeating this, 2q squared will be 4r squared. And then, of course, we can divide 2 out of both sides for convenience. So q squared is now 2r squared. Ah, now we're back to the same argument we did before. Since 2 divides the right-hand side, it must therefore divide the left-hand side, which means that q must be even. So by the same argument as before, q is even. So we have concluded the following, putting it all together in one place. Thus, P and Q are both even numbers. So they share, among other things, they may share something else, but they certainly share a factor of 2. But wait, that's a contradiction. Why is that a contradiction? Well, we assumed originally that P and Q had no factors in common. And now we have proven, under the assumption that square root of 2 is rational, we have proven that P and Q have a factor in common, the factor 2. Okay? So this is a contradiction because, just to get it on paper here, we assumed P and Q had no factors in common. Well, this all derived from the fact that we assumed that square root of 2 was rational. So, square root of 2 must be irrational. It cannot be rational because if it's rational, it leads to that contradiction. And that's it. That's the proof that square root of 2 is irrational. That's all there is to it. So I hope you enjoyed that. Now for a proof that's a bit more unusual, something you may not have thought about before. It's about comparing two infinite sets of numbers. Let's do this first. This is going to be a proof that there are the same number of rational numbers as natural numbers. Now think about what that means. The natural numbers are the numbers 1, 2, 3, 4, etc. The rational numbers include all of those numbers, but they also include every fraction. So you might suspect intuitively that there are more rational numbers than natural numbers. Unfortunately, that's not true. There happen to be exactly the same amount, and I'm about to prove that to you now. So, the first question one should ask is the following. How do you compare two infinite sets? I mean, they're infinite after all, so we need to have some way of comparing them that makes sense. So how do we compare two infinite sets like the set of rational numbers, which we've denoted by q, and the set of natural numbers, which we've denoted by n, boldface n. And I've got two infinites, so I mean two infinite sets here. There we go. Two infinite sets like q and n. Well, the answer is the following. We first ask the question, how do we do it for finite sets? And then we'll generalize that principle to infinite sets. So first, how do we know, this is time to think about this, how do we know that the finite sets, and just for an example, the finite sets say, I'll just take these two, A, B, C, and the set containing 1, 2, and 3, how do we know that they both have 3 elements? Okay, so how do we do this? What is the principle that you've known since grade school? Well, here is the principle that we actually do use, and here's what we want to remark upon so that we can use it for the infinite case. What we do is we exhibit what's called a one-to-one correspondence. And if that's too long, a phrase for you, we can call that a matching. If you like, matching's just as good, as long as we know what it means. One-to-one correspondence, or matching, we exhibit that between them. And this is what I mean by counting, and this is how it works. 1, 2, 1. And what we do is we list on this side the A, the B, the C, and over here the set elements of the other set, 1, 2, and 3, and here is the matching. Let's suppose A is matched with 1, B with 2, and C with 3. Nothing is missed. Okay, that is the point. And so by that simple argument, that's how we know that two sets have the same number of elements. There is a correspondence we can make between them. Well, the same idea, the very same idea, is used to compare infinite sets. Now we have to be a little careful how we do it, but it works just fine to compare two infinite sets. Now this is due to a man named Cantor in 1874, so this is fairly recent as a mathematical idea, because people in the past were a little bit leery of dealing with infinite sets. So here is the actual theorem that we are going to prove here. The theorem is, and it just restates the title of this section a little bit more compactly, there are the same number, quantity, or the proper word is cardinality, but we'll just use number here. There are the same number of numbers in Q, the rational numbers, as in N, the natural numbers. And here's how the proof will go. What we must do is we must exhibit a one-to-one correspondence. Let's write that down. We must exhibit, we must show you a one-to-one correspondence between the sets. A one-to-one correspondence, that's the matching that we showed for the finite sets on the previous page, between Q and N. Well, there's one way to put this. Behold, I will now show you such a correspondence, and then I will show you why it actually is a correct correspondence. So let's first examine this. Okay? Here is the correspondence as I've pre-drawn. And I'm saying write Q as the following. And here's how my organization works. In the first row, I will write all the fractions box over 1 that have denominator 1. In the second row, I will write all the fractions that have denominator 2. In the third, the ones that have denominator 3, denominator 4 in the next row, and so on to infinity. Now, every fraction has a denominator that is a positive integer, like 1, 2, 3, and 4, because, as you see, I can put the minus, if the fraction is negative, on the top number, which I will do throughout here. Now, what am I doing as I move through here? I'm moving through all the positive and negative integers. I start with 0, which is special, so it's off by itself, and then I have 1 and minus 1, 2 and minus 2, the next will be 3 and minus 3, all the way out to infinity. Same thing here, 1 and minus 1, 2 and minus 2, etc. And you see I repeat that across the top. So by this organization here, what I have is a kind of triangle, or a rectangular array. If I start at this corner up here, and I go off to infinity to the right or down, I get every rational number. Now you may notice that there will be repeats as I go. That's okay. I am getting all the rational numbers, possibly with repeats, like 2 over 2 is the same thing as 1 over 1, and that will be the same thing as 3 over 3 down here, and so on. 2 over 4 will be the same thing as 1 over 2. Now, how will I actually count this to show you that there are the same numbers here as with the natural numbers? Well, it works out pretty easily. I will start here. This will be what I will relate to the number 1 in the natural numbers, and then I will go in this fashion. I will then relate this one, come down here, and this one correspond. Then I will go back up here, pick up this one, go over here, pick up this one, come down here, pick up this one. All of these have been different, by the way, as we go. Come down here to 1/4, start back up to minus 1/3, and then the next one here is a repeat, so I will go around it to the next one, and then I will continue on. So what I'm doing is a kind of zigzag up and down through this corner of the rectangle, and you see by doing this I will end up eventually getting all of the rational numbers. So that is the process here by which I relate Q to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc., the natural numbers. So the correspondence that I get, if you were to write it out, or begin to write it out, just linearly like this, will look like this. Here is Q, and down here is N, and the order in which I did those was 0, 1, 1/2, -1 simplifying 2, -1/2, 1/3, etc. And I was associate that with 1, 2, 3, 4, 5, 6, 7, etc. And there is the correspondence that I said I would get, the matching between the two sets. And that matching clearly covers all of Q, and the natural numbers are always going to count up to the very end of those. And so we have shown the one-to-one correspondence, and so the proof is done. This is all I was required to do. So with that, I will leave you and come back with another proof comparing infinite sets. Now I'll show you an even more surprising comparison of two infinite sets. It's this comparison. This will be a proof that there are more real numbers than natural numbers. Now you might have suspected from the previous proof that I showed, where I showed that rational numbers and natural numbers have the same size or cardinality, that all infinite sets are going to have that property. Well, it's not true. There are infinite sets that are, in a sense, strictly more infinite or larger than other infinite sets. And the simplest one for me to show is that real numbers have more numbers in some sort of absolute sense than the natural numbers. So this is a bit surprising. I hope you enjoyed this one. All right. First thing I want to recommend is that if you haven't done it already, listen to the previous segment. The previous segment proof. Okay, because the ideas we use there will be repeated here. And again, this proof that I'm going to do is due to the same man as before. This man's name is Cantor. He did this in 1874. Okay, the first one to be able to think about infinity in this way. And this proof is even more exciting. This proof is even more surprising, let's say. Okay, this was something that at the time, certainly, and even now, if you haven't seen this, may surprise you. Okay, here's what I'm actually going to do. I won't attack the real numbers as a whole. I'll take a small subset of them. Watch this. There are more real numbers in the open interval from 0 to 1. That's all I need to check. In the open interval 0 to 1, then there are natural numbers in all of n. So I don't even need to compare all of the real numbers with n. I am just going to compare the numbers between 0 and 1, not including 0 or 1. Now that's really even more surprising, that a small interval like this alone has more numbers than the natural numbers. All right, here's the proof. And again, this will be a proof by way of contradiction. This will be the same kind of thing we did with the square root of 2 earlier. First, this is how the argument will go. First, we have to be able to talk about the real numbers that live in this interval from 0 to 1. So we'll talk about their decimal representation. So recall that all real numbers in that open interval 0, 1, which is this interval, by the way. Let me go ahead and draw the picture here. There's 0, there's 1. Talking about the interval that does not include 0 or 1, but does include everything that's in between. So this interval corresponds to that on the real number line. All the real numbers in that interval can be written as decimals, which we've seen before, as decimals of the following form, and I'll put that on the next page. And this will be crucial to our proof, because we want to be able to refer to all of these numbers so that we can match them, or at least try to match them, with all the natural numbers. And here's the form they take on. Point A1, A2, A3, dot, dot, dot. The A1, A2, and A3 will stand for digits, as I will mention in a moment. Or they might look like B1, B2, B3. I'm just using different letters to indicate that these are different numbers, C1, C2, C3. And this will be out to infinity, so that will go on forever. So this is how all of the numbers in 0, 1 look. They have nothing to the left of the decimal because they are fractions, after all, between 0 and 1. Where, just for the record, the A's, B's, and C's are all digits. Okay, they are all digits from the set of digits, which is, of course, the set 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, so those are all of the numbers in 0, 1 can be represented as these kinds of forms. Okay, I am going to claim, and this is something I'm going to hope to contradict, I'm going to make the following claim. In fact, I'll put here which we hope to contradict. Which we hope to contradict. Okay, this is this. I'm going to set this up and then knock it down. Here's the claim. The claim is there exists somewhere, somehow, a one-to-one correspondence, which again, if you like, you may call a matching, as long as you know what it means, a matching between these decimals that we just saw, these decimals in the open interval 0, 1 and n, all of n. Okay, that is my claim, and I'm hoping to be able to contradict that, because then I will have my proof. Well, okay, suppose we have such a one-to-one correspondence. We have such a matching, say, so that I can write it a little bit more simply. Suppose we have such a matching, as shown. Okay, I'll show that on another page here. And the matching, there's nothing particular about this matching. This is simply a 1, 2, 1 matching, as we've done before. And over here, I will have the natural numbers that I'm matching up. So this side over here will represent the natural numbers. And then over here, I will have all the decimals, which, if there is a matching, have to be listable like this: B1, B2, B3, C1, C2, C3, etc., going out to infinity. This represents the open interval 0, 1. And of course, here is the matching, or an example of such a matching, like so, and that will continue out to infinity. So if there is such a one-to-one correspondence, the natural numbers are listed here. All the decimals have to correspond back to them. So they have to be listable, if you will, just like that. Well, if this is a correspondence, a typical correspondence, I'm going to show that no matter what correspondence you have, there's got to be something over here that's missed. Some number in 0, 1 that this correspondence will miss. So what I will do is we'll now construct a decimal in that open interval 0, 1, which is missed by this correspondence, which is missed by this correspondence, or any correspondence. There's nothing special about this one. The only thing that's mentioned here is what is common to all the correspondences, that the right-hand side must be listable to compare to 1, 2, and 3. Okay, let me show you what the construction is. Let me build the decimal I said I would build. So we'll construct the following. We'll construct the number x, which will be the decimal point x1, x2, x3 out to infinity. So this is the decimal I'm about to construct. Now let me tell you how I'm going to choose the x1, x2, x3. Where x1 is any digit at all, but it is not equal to a1, as on the previous page, which I will bring back. It is also not equal to 0 or 9, and I'll explain that in a moment. Then x2 will not be equal to b sub 2, or 0 or 9. Similarly, x3 will not be equal to c sub 3 or 0 or 9. And we continue this until I get all the decimals out to infinity. Now, let me go ahead and tell you first of all why I am forbidding 0 or 9. We forbid, and I'm constructing this so I can make this any way I want, we forbid 0 and 9 so that, first of all, x will not turn out to be 0.000 out to infinity, which is 0. And 0 is not in the interval, that's one endpoint. Also, we don't want x to be equal to 0.999 out to infinity, which of course is equal to 1, and that's another endpoint. And x is not ambiguous in its representation. Ambiguous. Such as, like, for example, 0.4999 out to infinity is equal to 0.5. We don't want to have an ambiguity so that x in one form might not be there, but its other form might be there. We want to make sure that x is represented only one way. Now, why did I not make them equal to A1, B2, and C3? Well, look back here. Remember that these were the first three in my particular listing here. I'm saying that x1 is not equal to A1, x2 is not equal to B2, x3 is not equal to C3. So that's going to make x different from this one, and this one, because it differs in at least one decimal place. So let's see what sort of conclusion we can draw from that. Let me write down what I've got. But now, by the design or the construction, clearly we have that x is in the interval 0, 1. It's a decimal. And yet, x, which is point x1, x2, x3, etc., and I'll write this out this way, differs from the first one, point A1, A2, A3 out to infinity in the first decimal. So it differs right there, as I mentioned on the previous page. So it differs in the first decimal. It also differs from point B1, B2, B3 in the second decimal right here. So it's not equal to that one. It differs from, you see where this is going, C1, C2, C3 out to infinity. It differs in the third decimal. So it doesn't equal that one, so that they cannot be the same decimal. And this goes on forever. Well, that means that x is missed by the correspondence. Missed by the supposed, see, we now are suspicious of this, supposed matching. Okay, the supposed matching. Meaning, since the matching or that correspondence was arbitrary, it means that the claim that we had above is contradicted as we hoped. Well, if the claim is contradicted, what does that mean? Well, the claim was that there was a correspondence, therefore, thus, 0, 1, and hence all of R is a strictly larger set than n, the natural numbers. And that's the end of the proof. We have shown that the real numbers, in fact, an interval of the real numbers, is alone strictly larger in an infinite sense than the natural numbers. So that's rather surprising. And it shows us that there's more to infinity than perhaps you have realized in the past. So I hope you enjoyed that. Now, for Unit 2, more possibly for Unit 1, depends on where you would like to do this, here is a little enrichment topic that you might find interesting. I call it Algebra for Science. It's the notion of variation. So let's talk about what that might be. In science, of course, any of the sciences, physics, chemistry, etc., you are talking about various quantities in algebraic expressions. So let's let, say, x and y be any two quantities, And these could represent all sorts of things in physics, for example, and I'll show you some of those. Let x and y be any two quantities, and let's take a real number k in the real numbers, and make sure that it is a non-zero real number. Okay, I'm going to define now various sorts of variations. We'll start with first one, A, part A, I'll call direct variation. Now this is terminology that is used in the sciences. It's not particularly a mathematical topic in that the terminology is really what's important here. The mathematics is fairly simple, as you'll see. Direct variation. We say the following. Here are the phrases that are used. We say y varies directly. Y is one of the quantities. Y varies directly with x. We say it that way, or we say that y is directly proportional. Directly proportional to x. So there's another phrase. If what happens? If y is a multiple of x, so y equals kx. Now, of course, you know what this is as far as a graph goes. It's simply a line, and since there's no intercept indicated here, this is a line that passes through the origin. Now, a piece of terminology, either k is referred to as the constant of proportionality. The constant of proportionality. And that will change in various sorts of formulas, of course. Proportionality. There is an older symbol for this, by the way. This is the mathematically correct way to write this. There is an older way that this is written, and I'll put it down here. The older way is to say that y is proportional to x, with that funny little symbol there. And that's no longer used because we've adopted the equal sign, and this is far more easy to work with. But you'll see this very often used by folks in the sciences when they first want to say that something is directly proportional. They'll write this, and then they'll immediately go to the equation form. So that's what direct proportionality or direct variation is. One variable is simply a multiple of the other one. Okay. Here is the second definition, definition part B, and this is inverse variation. Inverse variation. Now you probably can guess where this is going to go, but let me write it out. Inverse variation. Here is the phrasing that we use here. We say y varies inversely with x, as opposed to directly with x. Y varies inversely with x, or we say y is inversely proportional to x. Proportional to x. There we go. If what? Well, if y is equal to k over x. So the x is now in the denominator instead of being on the top. So this is what inverse variation is. And of course, this is the constant of proportionality again. I'll even write it out, proportionality. Okay, just as before, it's called the constant of proportionality. And the old symbol, okay, the older way of writing this is that y is proportional to 1 over x. That's the way you might see it sometimes. But the equation, of course, is far more useful. It brings in all the mathematics you know. You may also recognize from your experience, if you're doing this after Unit 2, that this is the y equals 1 over x curve simply multiplied by a constant, so that the graph of this will be fairly easy to see. All right. Before we talk about the third category of variation, let me show you some examples of these first two, the direct and the inverse variation. So here are some examples from the sciences. And first, let me talk about direct variation. For example, here's a formula, P equals KT. And this is true for constant volume, say V. Okay? This is pressure, and this is temperature T. And pressure is simply a multiple of the temperature. For example, think of a pressure cooker. In a pressure cooker, the volume does not change. If you increase the pressure, the temperature will go up. if you increase the temperature by putting it on a stove, for example, with the cover on, the pressure will go up. So this is a fact from physics. Here's another one from physics. F equals ma. This is famous because it is what's called Newton's second law of physics. And it means force is equal to mass times acceleration. So if the mass is constant, this becomes the constant here, and so force is proportional to acceleration, directly proportional. Here's another famous one, F equals k times, say, d. This is an example of what's called Hooke's law. Now, Hooke's law governs springs, and the F is the force required to stretch or compress a spring through a distance d. And this is the constant of proportionality, often called the spring constant here. And as the constant grows, the force grows higher. So thicker, bigger springs are harder to compress or stretch than smaller, finer ones. And so on. Okay, those are examples of direct variation. Here are some examples, two examples, say, of inverse variation. P is equal to K over V. And this is in the situation where we have constant temperature. Constant temperature, big T. Now these are the same variables as over here, except now if the volume increases, the pressure will go down, assuming constant temperature. So if you have a balloon that you've blown up and then you blow it up to hundreds of times larger, it will not stay inflated because the pressure has gone down. The volume's gone up, the pressure's gone down, and vice versa. This is inverse variation. Here's another one that's a little bit more unusual. W equals K over L. And the situation here is that you have, and I'll draw it bent, a board. Okay? Imagine you have a board, say, made out of pine or something. And there is a weight that is put at the center of the board, and the board is supported at the ends, say. And the L represents the length of the board. Now, if you think about this, as the weight increases, the board is going to bend more. And so, depending on the length. If it's a short length board, it won't bend as much. If it's long, it will bend even more. So this weight is related to the length of the board this way. If the length increases, the weight goes down. And if the length decreases, the weight goes up. So there is a relationship between those, and there's some interesting formulas from physics. Let's now go ahead and look at the case that is a combination of the previous cases. So it's sort of a grand collection category, sometimes called joint and combined variation. And this is really just an extra category where we don't really need any more than A and B. But if we put them together, we can get these sorts. So this is when you have more than just the two quantities. You might have 3 quantities or 4, etc. There are 3 of these, and the first one I will call jointly, and this is direct version of jointly. This is where y is equal to k, but instead of just being times a single x, it might be times x and x2 all the way up to xn. There may be several variables here instead of just the one. So y is directly in direct variation with all of the variables, not just the one. So that's direct variation jointly. Of course, once you have that, you can see that there might be a jointly inverse variation. And of course there is. That would be where y is equal to k over not just one variable, but possibly 2 or more. So this would be varying jointly inversely. And finally, there's the combined variation, where you might have y equals k, I'll put it out front, times, well, there might be one or more variables on top. There could be just one, but there might be one or more, and x1 to xn will represent those, and then say z1, z2 up to zn will represent the bottom. So the top represents direct variation, the bottom represents inverse variation, and since they're both present, this is referred to as combined variation. Okay? And the x1, x2, xn, and the z's are all various quantities, and the k, as usual, is non-zero. So let me show you some examples of this. These become more interesting in physics and chemistry, etc., because very often there are several quantities involved, not just two. The examples here, I'll just give you two. Volume is equal to K times temperature over pressure. This puts together all of the various examples I had before for direct and inverse variation. This does not assume constant temperature or constant pressure or constant volume. These are the relationships between those two. Here's another one. L, this is a little bit more interesting for those that live in houses. L is equal to K times AT over little d. Now what do these represent? I'll go ahead and show you in this case. Let me box that in there. A is equal to the area. So A is equal to the area of the wall. We're talking now about a wall of a house. A is the area of the wall. T is equal to the temperature difference between the inside of the wall and the outside of the wall, like the inside of your house in winter and the outside of the house. D is the thickness of the wall, and L, what you're computing there, is the loss of heat. And the constant of proportionality is determined by experiment. But here's a relationship that says if the loss of heat is some multiple of the area of the wall times the temperature difference divided by the thickness of the wall. So this is an interesting example where we have 1, 2, 3, 4 quantities involved. And in physics you'll see several sorts of things like this. Let's do a couple of examples here just to show you how one might work with these. Here's one I've written out for me, so I don't have to spend the time writing it for you. The volume V of a sphere varies directly with the cube of its radius. So it's not just the radius. This will often happen when you're talking about variation. Sometimes it won't be just the variable alone. It may be the cube or the second power or some other power of the variable. It varies directly with the cube of its radius, and the constant of proportionality is given to us to be 4 pi over 3. Well, that means volume is equal to constant of proportionality 4 pi over 3 times, this is direct variation, r cubed, where r represents the radius. That's it. All I wanted to do was write down a direct variation, and now I've done so. Here's another one. These take a bit to write out, that's why I've written it out beforehand. Here we have the force F required to maintain an object in a circular path varies by experiment directly with its mass and the square of its speed v. And it varies inversely with the radius r of the circular path. And we're given that the constant of proportionality here is 1. So with that information, it's just a matter of writing this down. The force is equal to constant of proportionality 1 times direct variation with the mass and the velocity squared and inverse variation with r. And that's it. That's all that needs to be written down if you wanted to just examine direct variation and inverse variation here. All right, here is a final example in which we have to do a little bit more calculation. The weight W of a body above the surface of the Earth, like our bodies for example, varies inversely with the square of its distance r from the center of the Earth. Now let's suppose a given body weighs 55 pounds when it is 4,000 miles from the center of the Earth. Now if that's true, how much will it weigh when it is 4,400 miles? 4,400 miles from the center. Okay? Why don't you go ahead and try that, and I'll come back in a moment and show you what I did. Well, the first thing we should do in this is write down, in general, what we've learned from the statement about the relationship between the weight and that distance. So in general, we learned that the weight W is equal to some multiple over the distance squared. That's inverse variation with respect to the distance from the center of the Earth, r, squared. Now, in this problem, we are given that 55, when you have 55 pounds of weight, that's equal to k over 4,000 squared, because we are told 55 pounds at 4,000 miles from the center of the Earth. So from that immediately we get that k is 55 times 4,000 squared. And of course, once again, I'm not going to do any multiplication I don't have to do until the very end of the problem. So with k then, I can write specifically, here I had the general form, but k was unknown. Now I know what k is, I can write specifically what the formula is. So I now know that w is equal to specifically 55 times 4,000 squared over r squared. Now I can answer the question I was given. If r is equal to 4,400, if you are that many, if you're that distance above the Earth, and that was measured in miles, if you're that many miles above the Earth, then, using the formula, w is equal to 55 times 4,000 squared over 4,400 squared, putting the r in. And of course, if you put that in your calculator, you'll get 45.45 pounds, which is lighter than the original 55 pounds, which is what you expect as you move further and further away from the center of the Earth. So with that, we'll stop this small segment on variation, and we'll go on to another one. Now, this segment is one, as you see, for Unit 4, and it has to do with finding certain kinds of zeros of a polynomial. How can you find rational zeros, if any, of a polynomial function? The reason it wasn't in Unit 4 proper is because it's a really specialized technique that's not very useful in general, although it's nice and mathematically interesting, so I thought I'd put it in here so that you'll see how it works. All right, how do you find the rational zeros, if any, of a polynomial function? First thing I want to note is the specialized nature of the result we will eventually show you. The results here, and I'll repeat this later, the results here apply only to, well, they're always real polynomial functions, to real polynomial functions. But here is the interesting point, the point that's different and not general. Only applies to real polynomial functions with integer coefficients. So this only applies to the integer coefficient case. So if you have coefficients that are fractions or coefficients that are irrational numbers like square root of 2 or pi, etc., this will not apply. So this applies to those with integer coefficients, meaning, just to remind you, from z, the set of integers, which is the set 0, plus or minus 1, plus or minus 2, etc., out to infinity. So that's the first point to be made about this result. Now, in order to show you how this works without doing the proof in general, let me give you the idea that lies behind this. And the idea I will show you in the n equal 2 case, which is the first case where it becomes interesting. And the n equal 2 case is when we have a polynomial of degree 2. So we're talking about ax squared plus bx plus c, and we're assuming that a, b, and c are in z, the integers. Okay, so that's the situation we have. Now we ask the following question about rational zeros. What properties would a rational zero, okay, a rational zero of our f of x here, a rational zero, say p over q, where p and q are out of the integers, have? Okay, what properties would such a rational zero, get my 0 there, have? Okay? Now, we will assume, for the purposes of keeping things clean, we'll assume right from the start that we're only looking at p over q in lowest terms. That is to say, so P and Q have no factors in common. Okay, we'll assume they have no factors in common. So we're dealing with the simplest possible version of the zero. Okay, well, the answer is the main property can be found this way. Since P over Q is a zero of f of x, we have the following. If it's a zero, then it needs to satisfy f of x, which means it can make f of x equal to 0. That's what 0 means after all. So that means that 0 is equal to a times the 0 here, p over q squared, plus b times p over q plus c. Okay? That's what being a 0 means. Well, let me multiply this out. What I have then is a p squared over q squared plus bp over q plus c, period. Now let me do a little bit of algebra here. Let me multiply through the entire expression by q squared, which is that largest common denominator. And I then get 0 is equal to a p squared plus bpq plus c q squared. Okay, that's what I end up with. Now I'm going to modify this in two different ways. And let me see if I can schematically indicate that. First of all, I'm going to take these two terms and move them over to the other side. And I'll call that version 1 that I want to modify, leaving ap squared alone. Then in the other one, I will take these two terms and move them over to the other side, and I will refer to that as version 2. That will leave cq squared alone. So I'm going to do that on the next page. First I'll do 1, and then I'll do 2. So here I want to observe what happens in each of these cases. For 1, if I move those across, I end up with ap squared being isolated, and on the right I have minus bpq minus cq squared. And on the right I can factor out the common factor q, so I have q times minus bp minus cq, period. Now observe from this. Q divides the right-hand side, okay, because q is a factor there. Therefore, it must divide the left-hand side because the left and the right are equal. Now, q cannot divide into p because p and q have no factors in common. Therefore, q must divide into a. So, q divides a. And remember what a was. A was the leading coefficient of our polynomial of degree 2 here. Okay, so we've learned that q divides a. For 2, that's where we isolated cq squared. So we got cq squared is equal to then minus ap squared minus bpq. And on the right, this time I will factor out the p. So p times minus ap minus bq, period. Now look at this. Since p divides the right-hand side, p must also divide the left-hand side. But p and q have no factors in common, therefore p must divide c. So p divides c, and what was c, remember? C was the constant term, or the constant coefficient, let's call it constant term. So what we've discovered is that if, in this little idea generation, that if p over q is a root, or a 0 of our polynomial, then the bottom divides the leading coefficient and the top divides the constant term. And that works in general and leads us directly to the following theorem, which is what this section is about. This is called the rational zeros theorem. Rational zeros theorem. And it goes like this. If, now we have to write out our real polynomial in general, so we've got that again. If f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 down to a sub 1 x plus a sub 0, where, as usual, n is equal to 1, 2, 3, etc., and the leading coefficient is non-zero, and we continue with properties we didn't have before. We assume now that the constant term is not 0, and we assume further that all of the coefficients, an, n minus 1 down to a0, are integers. So I'll even box this part in because that is totally new. We haven't had that in a statement of a theorem about polynomials before. If we have all of that and we are looking at p over q in lowest terms, of course, p over q in lowest terms is a rational zero of our f here, then what do we conclude? If we have such a rational zero, we conclude that the top of it, p, must divide a sub 0, which is the constant term, and it must also be true that q, the bottom, divides a sub n, the leading coefficient. Let me write that again. A sub 0 is the constant term. That's what the top needs to divide. And a sub n is the leading coefficient. That's what the bottom needs to divide. So we can use this theorem, which I will not prove in general. We can use this theorem as a way of discovering various rational zeros, because every rational zero has to have this property. So if we look at all the numbers that divide a sub 0, they are potential numerators or tops for the rational zeros. And if we look at all the divisors of a sub n, we find all the potential denominators or bottoms. Now, in addition to that theorem, I'm going to give you another theorem. I'll call it the handy no rational zeros theorem. Now, this is one that you don't often see in this course, and I think it's a very handy theorem. And since the rational zeros theorem, as you will find out, can be quite tedious to apply and check, this at least will give you the chance to find out if there are any at all worth checking. So here's how the theorem goes, this no rational zeros theorem. If f of x is as given above, so we're talking about a real polynomial whose constant term is non-zero and all of whose coefficients are integers, is as given above, and the degree of f is greater than 1, so the only case left out is the linear case, so it's got to have degree greater than 1 for this theorem, and a sub 0, the constant term, a sub n, the leading coefficient, and f of 1, which when you think about it, if you put 1 in for all of the x's, what do you get? You just get the sum of the coefficients, an plus an minus 1 plus all the way down to a sub 0. If all of those are, if those are all odd numbers, okay, if they're all odd numbers, then you can immediately conclude without any work that f has no rational zeros. Now, I won't prove this theorem either, but it is extremely handy, as you can expect, because it's very easy at a glance to see if a0 and an are odd, and f of 1 is just add all the coefficients together. That's not very hard either. So it's very easy to check whether this condition is met, and if this condition is met, then the function has no rational zeros, so you need not bother looking for them. All right. Once again, here is the basic idea for looking for rational zeros if you want to do that. If this is your polynomial f of x equals a sub n x to the n plus dot 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 plus a sub 0, and if you have p over q sitting here being a rational zero, then what must happen? The p must divide, it divides a sub 0, and the q must divides a sub n. Okay, so if you have a rational zero like that, that is what has to happen, and so that gives you the test for checking rational zeros. Now, my recommendation on using these two is, the first thing is check the second theorem first, because if there are no rational zeros, you don't want to spend your time looking for them. So check the second theorem first, and let me warn you, the list that the theorem allows for, the list of candidate zeros, candidate rational zeros, is often very long. Okay, we'll do a simple example here, but as you'll see, even in this example, things are quite tedious, which is the reason that this technique is not used all that often. So here's my example. List all the candidate, I'll call them candidate, you can call them proposed zeros, etc., or possible zeros, the candidate rational zeros of the following: f of x equals 2x cubed plus 11x squared minus 7x minus 6. And when you're done with that, check which are actually zeros. Okay? So let me box in my polynomial here so it'll stand out from that. The solution. All right, what do I want to do here? I want to find out all the candidate rational zeros. Let me notice a couple of things before I go on. This is a cubic polynomial, polynomial degree 3. Now that's fairly small, so we should expect, based on our knowledge of zeros, no more than 3 rational zeros. In fact, based on the pictures of cubics, we expect either 1 or 3 rational zeros. So, just keeping that in mind, let's go ahead and see if the rational zeros theorem applies. The coefficients, all integers, as you see, 2, 11, minus 7, and minus 6, so the theorem will apply. We also see that an is not 0 and a naught is not 0, so the theorem indeed applies. Now we know that p of a potential p over q rational zero, p must divide, or divides, a sub 0. So what are the candidates for p? All the divisors of a sub 0 minus 6. Those would be plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. And let me point out here, don't forget the negatives. Don't forget the negative cases. Okay? Because negatives can be rational numbers. They can be the top of a rational number. Now, finding all of these sometimes can be hard. If the number is rather large, you might have to do a lot of extra work to get all the factors. This one was easy. And then also q must divide a sub n. Well, a sub n is 2, so this is a little easier. We know that plus or minus 1 and plus or minus 2 will then divide that. Now, of course, we're not interested in p or q alone, so we are interested in p over q candidates. So the candidates for p over q are taking these p's over these q's. Well, first of all, any of the p's over plus or minus 1 will preserve these. They'll change the sign, but we have plus or minus, so it'll become minus plus. So these over 1 will give these back. So we'll just repeat all the integers there. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Then the p's divided by the 2's will preserve their plus or minus. But let's see, we gain some new ones. 1 over 2 gives us plus or minus 1/2. 2 over 2, of course, is 1, which we already have. 3 over 2 is a new one, plus or minus 3/2. And 6 over 2 gives us 3, which we already have. So here are all the candidates for rational zeros. That's 1, 2, 3, 4, 5, 6 times 2. That's 12 candidates. Now we know that at most 3 of these are correct. It would be very tedious to try and substitute every one of these into the original expression. So I'm going to use what other information I know to help me reduce the tedium. So it's tedious to check 12 candidates. So we graph the function to help narrow our choices. Now if you graph this is the window I use, minus 7,3 by minus 1070. If you graph our cubic, here is the picture that I got. Here is the axis. There's another axis. I come up here and it goes like this and then comes down there and goes up there. So it looks like I have 1, 2, 3 zeros. And if I then use trace or some other means, I see that this is approximately minus 6 this one is approximately minus 0.5, and this one is approximately 1. Now those are all members of my collection of rational candidates. This is 1/2, minus 1/2, this is 1 and minus 6. It turns out, if we check these, that they all work. F of minus 6 is 0, f of minus 0.5 is 0, and likewise f of 1 is 0. So the only 3 rational zeros are those, and that covers all of the zeros, so we're done as far as finding zeros go. That eliminated 9 candidates. So using graphing or any other technique in addition to what you already know may help. All right, let me do one example to show you the advantage of that second theorem. Here's my example. And the question is, any rational zeros? And here is the polynomial f of x equals x to the 5th plus 7x to the 4th minus 28x cubed plus 125x squared plus x, and finally minus 3,275. Now, no one in his right mind would want to try the rational zeroth theorem on this, because you would be looking for all the factors of 3,275. So the smart thing to do is to see if there are any rational zeros at all using that second theorem. So let's observe that A5 is equal to 1, which is odd, okay? And A sub 0 is equal to minus 3,275, which is also odd. And then let's look at f of 1, which remember is just, when you put 1 in for x, you're just adding the coefficients. So the sum of the coefficients is 1 plus 7 minus 28 plus 125 plus 1 minus 3275. And if you drop that in your calculator, you get minus 3,169, which is odd. So all of these are odd, which means the conditions of the theorem are met. So there are no rational zeros. Therefore, you need not check all of the divisors of 3,275, because that would be very tedious. Okay, on that note, I will leave this little segment. I hope that added to your knowledge from Unit 4, and then I'll have one more segment to show you. Now I'm going to show you something that I've got listed here for Unit 7. It actually addresses a topic that first appeared in Unit 5, but only in Unit 7 did we get the techniques for actually proving the following statement. We're going to prove that E, the number E, is irrational. Now, I stated it was irrational in Unit 5. Now we have the tools to prove that. So let's go ahead and do that. First, let's recall that E was, remember what we did with E, E was the base of the natural exponential function. Okay, and it also then became the base of its inverse, which was the natural logarithmic function. The previous definition that we had of E, I want to remind you how we defined it. This was the previous definition. We said that as n goes to infinity, as n grows without bound, the object 1 over 1 plus n to the nth power goes to E. Okay, that's how we defined it. We defined it as the end result of this as n goes to infinity. Now I'm going to derive first, before I do the proof, I'm going to derive another definition of E, because that's the one I will use in the proof. And I will derive it based on what you know. So this will be a derivation of a second definition of E. The E is so important, it can be defined in several different ways, and you're going to see a second one now. A second definition of E. All right, let's use what we know now. By the binomial theorem, which was the last thing we did in Unit 7, by the binomial theorem, if we take that expression 1 plus 1 over n to the nth power, that after all is a binomial, we can write it out as the sum of the n choose j's, where j goes from 0 to n, of the first term is 1, so 1 to the n minus j, times 1 over n, the other term, to the jth power. Now, what does each summand there look like? Well, it's n choose j. The 1's, of course, I can drop out because that's just 1. And the 1 over n to the j I will rewrite as 1 over the quantity n to j. Just put the j on the bottom. Now, first of all, these can be simplified. Okay, and with the simplification will come what we need to work with. So first of all, let me simplify that. And that'll be just a little bit of work here with factorials. So I'll rewrite it again. N choose j times 1 over n to the j power. Now this is the object I'm going to simplify now. Well, that is, first of all, by definition, n factorial over j factorial n minus j factorial times 1 over n to the j power. Get my j power in there. Now, let me rewrite this as follows. 1 over j factorial, I'm taking the j factorial out, and then I'm dividing the n minus j factorial into the n factorial. Now, we've done that before. That will leave us with n times n minus 1 times all the way down to the 1 right before n minus j, which will be n minus j plus 1, the one right above that, times, and then the last one is 1 over n to the j, I just repeat. Now in here, let me observe that in here I have j factors. If you count the factors, there are j of them. I have n to the j out here. Now I'm going to divide the n to the j up into n times n times n, etc., j times, and put one n under each one of these. So I'll have 1 over j factorial times n over n times n minus 1 over n, and so on, till the end, n minus j plus 1 all over n. And that's my new representation. And finally, I will write this one last time, which will make everything crystal clear, I hope. The n over n, of course, is 1. And I will write these by dividing the n into the top. So n minus 1 over n is 1 minus 1 over n. And so on to the end. The last one becomes 1 minus j minus 1 over n, as this divides into there. So, if we stop there, we see that I've rewritten this first object as this long object. What was the advantage to doing that? So, as n goes to infinity, we see that the original object up here, which is now this, the original object n choose j times 1 over n to the j, approaches, as n goes to infinity, well, what happens here? As n goes to infinity, this goes to 0. And in fact, the second terms in all of these go to 0. You're left with a bunch of 1's. Well, all of those 1's just give you plain old 1 over j factorial left over. Okay, with that calculation, that this object is this object as n goes to infinity, watch what I can do. Hence, as we let n grow to infinity, we have two things. We have both the earlier fact that 1 over 1 plus n to the n goes to e. Okay, that's known. And now we know that 1 plus 1 over n to the n, which can be written as the sum of the n choose j's times 1 over n to the j's, where j goes from 0 to n, under n going to infinity itself goes to the sum of the j equals 0 to infinity now of the 1 over j factorials. Because remember, this part, as n goes to infinity, just goes to that. That's what we just showed. But what is this? This is equal to 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial, etc. In short, this e and this expression here must be the same because they are the result of 1 plus 1 over n to the n going as n goes to infinity, going to each of them. So the conclusion is that e is equal to 1 plus 1. I'm writing 1 over 0 factorial as 1, 1 over 1 factorial as 1, plus 1 over 2 factorial plus all the way out to typical term 1 over n factorial plus out to infinity. So there we have a new expression for e based on a little argument using the binomial theorem. And that's what I'm going to use in the proof. So speaking of the proof, let's do it. Theorem. As you expect it to say, it says E is irrational. And here we go. Proof. Well, we start out by recalling what we just wrote down, that E is equal to 1 plus 1 plus 1 over 2 factorial plus up to typical term 1 over n factorial plus out to infinity. And so we can let S sub n, the nth partial sum, be 1 plus 1 plus 1 over 2 factorial plus up to 1 over n factorial, period. Okay? Partial sum always ends here at that point. So that's the nth partial sum. So then part 1 of the proof. Part 1 of the proof says then for any n, I'm talking about n equal 1, 2, 3, etc., we can write the following. And here is the entire argument for this first part. I like this argument. It's really quite nice, and it uses the notion of geometric series we talked about. 0 is less than e minus s sub n. Now that's certainly true, because s sub n is the partial sum of e, which is the infinite sum. So you take that away, you've got something left. That's positive. Okay, equals, and then what's left if you take that away? Well, you have 1 over n plus 1 factorial, because remember the nth partial sum ends with 1 over n factorial, so this is the next term. Plus, let me write out a couple more here, n plus 2 factorial plus 1 over n plus 3 factorial plus ... out to infinity. Now, let me factor that by taking out the 1 over n plus 1 factorial. Okay? What's left? 1 plus 1 over n plus 2, because this is just one number beyond n plus 1 factorial, plus this one is two numbers beyond, so it's 1 over n plus 3 times n plus 2, plus ... out to infinity. Now here is a crucial step. This, I claim, is less than 1 over n plus 1 factorial times 1 plus, and now I'm going to replace 1 over n plus 2 by 1 over n plus 1. Is that legitimate? Sure it is. I'm claiming that this is greater. I'm claiming that 1 over n plus 1 is greater than 1 over n plus 2. Well, sure it is. The denominator is smaller, so that means the fraction is bigger. Same thing here. I will make the denominator smaller by making the n plus 3, n plus 2 into n plus 1, n plus 1, which is n plus 1 squared. Plus, and I continue that process. But now we recognize that we have a geometric series here. So it's a geometric series, and the r for the geometric series is 1 over n plus 1. That is clearly less than 1, so that means we can use the sum formula we learned in a previous segment, that this is 1 over n plus 1 factorial times 1, which is the a here, over 1 minus 1 over n plus 1. So there's no more dots here going out to infinity. We have a nice summation formula. And the rest of this is a bit of algebra. We want to simplify all of this in short. So this is 1 over n plus 1 factorial times. Let's see what we get here. We get 1 over on the bottom. We're going to get a single fraction, denominator n plus 1. And we have n plus 1 minus 1 on the top. N plus 1 minus 1 is n. So I have n over n plus 1 on the bottom. Since this is a fraction, a reciprocal, it will flip over. So this is 1 over n plus 1 factorial times n plus 1 over n. Well, of course, the n plus 1 there and the n plus 1 here will cancel, leaving n factorial on the bottom. So this is now 1 over n factorial times n. So let me put this all together because this was a really long expression. We have e minus s sub n greater than 0 and less than this object at the bottom. So let me put that, like I say, all on one page so we can keep track of this. Thus, we have the conclusion that 0 is less than e minus s sub n less than 1 over n times n factorial. And I want to do one last little calculation. I'm going to take the n factorial here and just move it up to there by multiplying through by n factorial. So I end up with this. 0 is less than n factorial times e minus s sub n less than 1 over n. And that's what I wanted to conclude here. So this is my starred statement, that this funny number in the middle, this n factorial e minus s sub n number, whatever it is between 0 and 1 over n, and that's for any n. Remember, for any n, 1, 2, 3, etc. Okay, that's the result I needed. That's the first part of the proof. Now, I'm going to use that result to actually address the heart of the proof. 2, we will assume, as I've done before, by way of contradiction, that the opposite of what we believe to be true is true. We will say that E is rational. Okay? Say, to be specific, that E is equal to P over Q, where P and Q are in the natural numbers. We can assume positiveness because we know that E is a positive number. And we will assume in lowest terms, which means that P and Q, remember, have no common factors. Okay, no common factors. Okay, so we've made the assumption that E is a rational number in lowest terms. Now, let me show you what that assumption will lead to. We're hoping that it will lead to a contradiction. Now, first of all, let's choose our n that we're going to be using here. You'll see where the n comes in. We'll choose any n whatsoever that's bigger than the denominator of P over Q. So, certainly, no matter what we choose for that to be, certainly n is greater than 1. Q could be 1 or bigger, but it's not going to be less than 1. So certainly n is greater than 1. So if we flip both sides over, that means 1 over n will be less than 1. Now that's a small observation. Then, now we go back and we pick up 1. Then by 1, what do we have? We had 0 less than n factorial times that e minus s sub n less than 1 over n. This is the part we get back from 1. Now in this case, 1 over n is, by our choice of n, we could choose any n. We chose one bigger than q. We have 1 over n strictly less than 1. So what does this mean? Meaning, in particular, okay, look what we have here. Here is this funny number, n factorial e minus s sub n. Meaning in particular that that number, n factorial e minus s sub n, is not an integer. Okay? That is not an integer because what? It's because it's between 0 and 1. If it's between 0 and 1, there are no integers in there. So whatever that number is, it's not an integer. Okay, good. We know that that number is not an integer. All right. But here we have what? Let's look at that number again. N factorial e minus s sub n. There's that number. Well, e is assumed to be p over q here. That's the assumption we're hoping to contradict. But for the time being, we've assumed that it's p over q. So n factorial times p over q minus s sub n. And now let's just write this out a little further to see what we actually have. Running the n factorial through, I have n factorial times p over q minus n factorial times the nth sum, which is 1 plus 1 plus 1 over 2 factorial, 1 over 3 factorial, plus all the way up to 1 over n factorial. And now let me do a little rearranging. Let me rewrite this first part as n factorial over q times p. It's the same as the above, but you'll see in a moment why I wrote it that way. Minus, and this time let's run the n factorial through the entire expression, minus n factorial plus n factorial plus n factorial over 2 factorial plus n factorial over 3 factorial plus, finally, n factorial over itself, n factorial. Now observe here, recall rather, that n is greater than q. And now I can make the crucial observation. Stay with me. N factorial over q. N is bigger than q. So this factorial, which is n times n minus 1, etc., all the way down to 1, includes among its factors q, which means q divides into this, which means this is an integer. This times p remains an integer, minus, and I claim every one of these is an integer too. N factorial are certainly integers, and the same argument holds as over here. N factorial n is bigger than 2, so that 2 factorial divides into that. 3 factorial divides into this. N factorial certainly divides into itself. So the upshot is, whatever this entire expression is, and I don't care about the details, it is an integer. And there's our contradiction, because what is this all equal to? It's equal to this number here, which we claimed just a moment ago was not an integer, being between 0 and 1. And now we've claimed that it is an integer. This is our contradiction. And the contradiction arose because we assumed that E was P over Q rational. So there is only therefore one conclusion. So E must be irrational. And there you have it. That's the end of the proof. And I hope you enjoyed that. It's rare that you get to see how certain numbers are proved irrational. Square root of 2 is irrational was included here. And showing you that E is irrational turns out to be possible with just the information that you know from college algebra, barring a couple of minor difficulties. So I hope you enjoyed this, and that's it.